Alright, well we are Senior Design Group 10 and I'm Tyler Brewer.
I'm Michael Bigler.
I'm Hal Du.
And our project is a home automation system that we call LightX, and we were sponsored by Keepalo Inc. So with the guys at Keepalo, we came up with these requirements, and so the main focus was we can easily replace a light switch that already exists in a light switch box, and then we can dim and brighten lights, and the module will operate safely. We want our users to be safe, and with the high voltage line we needed isolated power supplies and safe wattage ratings for our design. The design will work throughout a house wirelessly, and we can control the lights on an actual switch on the control panel, and also we can control it from an app that's connected to the internet. And then the requirements for the app were it must be a cross-platform compatible web app. So this allows us to be used, allows the app to be used on any device, and it's also easily portable to Android, iOS, Windows Phone, whatever device you would like to use.
Alright, so as designer of the hardware and circuitry, my first main concern was how are we actually going to control the power of the light? How are we going to control it digitally so that it can be controlled through an app? So after some research, I found that the best option would be to use a triac. A triac is a device that won't conduct until you give a voltage at the gate. So as you can see on this graph, you'll have your AC voltage off your mains, and then once you supply a trigger, then it will start conducting. And then it will stop conducting whenever the voltage hits 0. So as you can see on that bottom waveform, it starts conducting and then the voltage hits 0 and then it stops until your next pulse. So it's a good way to control the amount of power going to your light. So if you did send triggers as shown in this waveform, it would be a little, or about a third of full power. But in order to use a triac, we have to know when are we hitting the zero crossing, how do we know when to give these pulses. So we implemented a zero crossing detector, which is an optocoupler. And you can see with the AC voltage on top here, you'll have whenever it's hitting or very close to 0, then you'll have an output pulse. And this will go to the microcontroller, so then it knows when are you hitting 0 and when do we need to give the trigger voltage to the triac. So I designed our PCBs, and here's the layout of the power PCB. You can see the triac is mounted onto the heat sink. If you're at higher power, then you can safely dissipate the heat, won't overheat. I also implemented a isolated 5-volt DC power supply, which will give the voltage we need to run pieces of the circuit and will give you a safe voltage so that the user manually hitting the buttons won't get shocked or anything. And then we have a triac gate driver. This is an opto-isolator. What this basically does is isolate the signal going from the microcontroller to the gate of the triac. And then the optocoupler I had mentioned for the zero crossing. We have circuit protection, which is just for the power supply. It's a fuse and a varistor. And then mounted onto the board are wire leads to the mains and then the output to the light bulb. And then here is how we assembled our design. The big part of our criteria was it had to be compact enough to fit into a electrical box. So Tyler made this white piece. He 3D printed our faceplate. This is the piece that we mount our buttons on and is the piece that is visible on the wall. And then you can see on the back of it are screw holes and mounts so that we can mount our PCBs onto the back of it. So you can see in the assembly on the left here, that's the back end of it, how our PCBs mounted onto the back of our faceplate. and it made it pretty compact. We could fit this into a 2-inch deep electrical box. And on the right we have our faceplate with the controls. On top is the button to brighten the lights, the middle is an on-off switch, and then the bottom is to dim the lights. And they also have LED indicators where there will be the green LED lit if the lights are on, and then the red LED lit if the lights are off.
Alright, so this is the kind of the main control board of our design. So you can see on there we have a surface mount microcontroller and also programming pins for easy access to program the controller. And over on the other side is a logic level converter and a voltage regulator for our radio, which is the XB component up there. A lot of our constraints were power, so we had your high voltage mains, step it down to 5 volts, and also 3.3 volt for the radio. So that was something that was kind of always on our mind, was power. How do we get everything power? So this takes the 5 volts off of the power board from Michael and regulates the radio and gives that to the microcontroller. So the main functions of the microcontroller are to actually control the dimming level. So it takes all the information reading in from the 0 cross, and it fires interrupts when it hits 0, and then we can delay a specific amount of time depending on how bright or dim you want the lights. And this algorithm takes in values from 0 to 100, and it uses that to smoothly dim the lights so the user has a nice experience brightening and dimming it. And this also monitors the hardware panel buttons, adjusting the delay timing and controlling the LED indicators. And this contains our logic for sending wireless transmissions to our base station. So we have this is like an individual node and then a base station. So this microcontroller processes the data off of the radio, and I'll go through that in further detail in a minute. It also receives the transmissions from the base station, updating the values and the statuses of the lights as it goes. So here's our wireless setup. We have a Raspberry Pi base station with an XB radio, and then this would be one of the light nodes that you would replace into your light box. And so these communicate to each other via radio transmissions. So here's an example of how we would address an individual node. So let's say over on the left you have your kitchen light, and we want to set it to 50%. So the app communicates with the base station through an internet connection, and then the base station will send out this node value. So each node has a corresponding unique value. So for this one, the example is 101. So it's stored that that value is 101, and so the base station knows that it needs to send 101 and then the value of 50. And then on this side, it's just going to read available data, and if it is its address, it takes in that data and sets the lights to that level. If not, it ignores the transmission and keeps looking for any transmission that is its value 101. So this allows us to have multiple nodes on a network, as many as we would need. So we need a place to store all of our data. We initially thought that it would be a good idea to store it all on the actual base controller, but this came up with problems of saving state, power loss, and it just wasn't a nice user experience. So we came up with this solution, which is called Firebase. It's basically an online storage database, and you can see we have our data fields here for our lights. This first number is just a unique Firebase ID that comes with Firebase. Next one is our actual dimmer state value. And there's the unique ID per node. And this would be the name of the node. Now the advantages of this is there's real-time updating. All of our devices and everything are always constantly looking at this database. So if anything changes on here, it's going to change across all our devices. It's very easy to manipulate data, and it also has a feature where it can host our static JavaScript and HTML files. And this is really nice because you can go to this URL on any computer and sign in from any device on there. Also allows us for username and password, it's secure, and it's extremely expandable. So for the actual base station design, this is what coordinates, this is what bridges the gap between the individual light nodes and this internet connected app. So we connected an XB to the GPIO pins on a Raspberry Pi, and then you would connect your Pi up to the Ethernet connection and connect it to the internet. And then there's an actual picture of our device. We have it in a nice box, and there's an antenna for extended range, so it can reach throughout a very large house. The range on it is pretty impressive. We put the XBs in a metal container and walked throughout houses and had basically no signal drop, so that was really good. So this Raspberry Pi runs Node.js, which is a framework that utilizes Google's JavaScript engine, and this allows for real-time networking, which is exactly what we want to do with this, and it's fast and light and works very well. So what this does is it's connected to the internet, so it just pulls our Firebase data about every 100 milliseconds, and it's going to compare that to what we've stored in our light system. So if there are any changes, it's going to send that out over the XB, and the nodes are going to change the value of the lights. It reads in dimmer level changes from the individual nodes, so when you change a value on the light switch, it sends that back to the base station, which sends it back to Firebase, which updates it on the app. So a lot of individual points here, but Firebase is kind of our main point that everything is looking at.
Imagine the situation when you get home at late night, it's all covered by darkness, and you can barely find a switch, and you can feel the tension from your heart within the darkness. For now, you don't need to worry about this kind of situation. For now, you can only open a single application, all your tension will go away. For now, life becomes easier. This is the primary goal for our bio group. We would like to build a home automation system. We call it LightX. Our system is based on the model wheel controller framework, which is implemented by AngularJS and Ionic framework. AngularJS is open source web application. It only requires HTML, CSS, and JavaScript. For the model wheel controller framework, the model notifies associated wheels and controllers. It allows the wheels to produce update output, and it also allows the controllers to change the command. For the wheel, it requires information from the model, and it also generates an output representation to the user. For the controller, it sends commands to the model for updating the model's state. It also sends commands to associated wheel to change the wheel's presentation of the model. This is the login page of our application. For the registered user, you only need to type your registered name and corresponding password. And once you've done it, you can just click the sign in button. We also provide the forgot password functionality. You can always find your account back. And we also have a create new account. This is the create a new account page. It has all your information. For how it works, it will post all your information to the Firebase, and it will store all the information on the Firebase. Once you've done this, you will transfer to the light control panel. This is under the Home tab. You can click the control pane. There will be a setup pane popping up from the bottom. You can see the total number of lights in your system. And once you click the add, there will be a new message popping up. You can add a new light by entering the light ID. And there's also an option called delete. It's highlighted in red since it's a dangerous option. you don't want to accidentally delay your light. And you can enter the light ID that you would like to delay. And back to the control panel, you can see all your details of the lights, the light name, dimmers, light bar, and switch. For the change light name, once you change your name, the name of the light will be updated globally. All your devices will be updated. This is the home tab, and also have the information tab, which is brief explanation of our project. And once you sign out, you're back to the sign-in page. Okay, how our software works. It will request by using HTTP GET method every 5 milliseconds, so all your devices will be updated. And for the HTTP post, it's like every time when the user make a change, it will post all the information to the Firebase. So all this information will be stored in the Firebase.
Yeah, so quick thanks to Caleb and Dustin at Keepalo for working with us throughout this project, and for Professor Kruger and Curry for all their consulting and advice. So are there any questions that anyone has for us?